Silvia had a question for Karl. Do you want to ask the question verbally, Silvia?
Yeah, thank you, Karl. It was a wonderful talk, and I wanted to know your opinion. What do you think this self-organization at the nervous system level is founded at the single cell level, at the neuron level, or even going back for every cell in our bodies at the gene level? So this gene organization comes from the gene structure organization.
Yeah, absolutely. I didn't introduce it in that presentation, but the link with self-organization comes from the study of non-equilibrium steady states in systems in physics. And the key thing is you have to introduce a separation or a boundary between the internal states and the external states of any system. In the very introduction of that boundary, under the assumption that the dynamics have an attracting set, then you get for free dynamics that optimize or do gradient flows on that function. And the picture you then have is basically what's referred to as these Markov boundaries or blankets, in the sense of J. Pearl, that enshroud each other at multiple scales. So the idea is exactly the same mechanics would be seen at the molecular level, that then they'd be seen in terms of intracellular organelles, and then the cell itself has a cell surface with a Markov blanket, and then a population specialized brain region, and then a brain as an organ, and then different organs in my body, and then so on to conspecifics, institutions, right up to gear, if you want. So in principle, if that hierarchical nesting of blanketed structures that enable a separation of states that are internal at that scale of description from the external states exists, then it has to be the case you can write down their dynamics as a gradient flow on that evidence lower bound. So then the question is really, what is the relationship between the blankets at different scales and blankets and blankets? But you're absolutely right. In principle, and indeed there are papers looking at dendritic self-organization, treating a single neuron as a system, and it learning to sample those presynaptic inputs that are the most predictable to, if you like, install in its sort of postsynaptic specializations some model of the contingencies and the inputs that it hears or sees from other populations.
Oren.
Yes, hello. Sorry for being late. So it's a question to Karl, really out of ignorance, and just how you see, I don't know how to call it, but maybe the free energy framework, how it relates to other approaches to intelligence, like so someone mentioned game theory, but maybe deep learning. So is it a more general framework, or do we have your competitive frameworks?
I would look at it as a more general framework. So it is not competitive. In fact, if there's something out there that works, that cannot be cast as usually a limiting or a special case of that sort of generic imperative, existential imperative from the perspective of the statistics of self-organization, then that's a problem for the free energy framework. So I think the clearest example of that is when I was talking about the ways of decomposing evidence and expected evidence, or expected free energy bounds on evidence, into things like risk and ambiguity, or intrinsic versus extrinsic value. So a limiting case of that is that there is just expected utility or intrinsic value as a special case, and then from that you can get economics and utility theory, or if you're in behavioral psychology, it would be reinforcement learning. Deep learning, as I understand it, is an interesting case in the sense that it would require you to specify what kind of deep learning you're doing. If you're doing a variational autoencoder, then that is under a very, very simple kind of generative model, exactly effectively a gradient flow, or at least a gradient, a coordinate descent on that objective function, the variational free energy. However, if you're doing deep RL and you're specifying the cost function or the value function, then that is still a special case, but there's no uncertainty about the weights or the parameters in your deep learning. That's really interesting, because if you don't have an evaluation of the uncertainty, someone was talking, I think Rosella was talking about uncertainty quantification on the weights of your deep network. You can't evaluate the marginal likelihood of the evidence for that network, and therefore you can't minimize the complexity, and that usually manifests in terms of sharp minima. So you have to resort to all sorts of tricks like mini batching and the like in order to sort of reintroduce that uncertainty that you've not been able to measure because you haven't got a belief distribution of the weights. So deep learning would be an interesting special case that has special problems that might be resolved by slightly more generic. And all that would require is putting posterior beliefs over the weights themselves. Does that make sense? I'm not sure whether you like deep learning or not.
Yes, no, thank you very much. It clarifies things. Thank you.
So, Oren, just out of interest, since you do work on Basin learning, do you not? Yeah. So casting the world as I do believe that there are ancient Basin Priors from which you would start, right? And I think the free energy people do believe, and I think Karl himself talks about embodied cognition, that it is embodied in ourselves, and that is used as the Basin Priors. But would that be enough for us to learn everything else that we would need to?
Yeah, I really don't know. I'm not doing any Bayesian learning, so I come from philosophy and logic, so yes.
Bill, many questions before what's happening now is because we've got time that Vincent's talk was.
Sheri, can I ask a question?
Yeah.
So, Karl, this is a question to you, and I think the theory that you're proposing is very fascinating in the sense that it's very generalizable, it seems. But from a kind of game theory perspective, my problem is that in this case, I do not know a lot about this particular strand in epistemological game theory. But I know that they take ambiguity aversion quite seriously. They have decision theoretic frameworks for that. So I was just wondering that even if I ignore the strategic interaction, and so purely in a decision theoretic perspective, I mean, just technically speaking, how is this different from regular, let's say, ambiguity averse agent who is performing in a Bayesian world? Exactly where does it differ from that? Because you're still using a basic Bayesian framework, right? If I understand correctly.
I don't know very much about economics, but if I'm right in assuming that in economics you can equip a utility function with an ambiguity or a cost function, then I would say that's a really nice example of the mechanics I've been talking about. So this is an example where the free energy formulation is meant to generalize stuff that works already. The only thing that the free energy formulation brings to the table, which might be interesting from your point of view as an economist, would be that's splitting into risk and ambiguity, or to something that is predominantly dictated by your prior preferences or your loss functions, and which would be the risk part of it. And then, on the other hand, the pure ambiguity, which has got nothing to do with what you want to happen. That carving into two is is just an interpretational thing. The underlying objective function is just one expression. It's basically an expected function or expected free energy, which tells you that there is, because there's only one objective function, it means that for any weighting of ambiguity, there is an optimal weighting of the risk. Sorry, to put it another way, there is always a Bayes optimal weighting of the ambiguity and the risk term. So that from my perspective is an interesting feature, because it means there is an optimal balance between these sort of more epistemic imperatives and these more utilitarian imperatives. Usually the way that's resolved practically in the using the formalism I was describing is by acknowledging that the different preferences or value functions, you cast those as a log probability of expected outcomes. So things that are highly valuable are the kinds of outcomes I expect to happen to me, and therefore they're unsurprising. But I will also have a precision about those beliefs. So I may believe I am going to be rich, but I may believe that with very small confidence or very, very great precision and confidence. So the entropy of the precision of your beliefs that define your cost function now becomes another free parameter that is learnable. And it's that tunes the, if you like, the balance between the ambiguity part and the risk part. So that opens up an interesting world, which speaks to the previous question about, can you start from any full set of priors? Not really in my world, because as soon as you start to equip a belief with a precision, raising a probability to the power of something or multiplying a log probability, you're suddenly introducing a hierarchical generative model. And as soon as you introduce a hierarchical generative model, there are no full priors, in the sense that any belief at an intermediate level in the generative model becomes an empirical prior, and now becomes learnable or updatable from the observation. So the question now comes is, where do your empirical priors come from? And in the application of game theory to try and phenotype people in psychiatry, say people who show addictive behavior, we try to estimate those precisions. How much do they value that outcome relative to the ambiguity? And I would imagine that you've got exactly the same constructs in looking at objective and subjective utility and isopreference and prospect theory. I imagine you've got very similar devices in economics to try and estimate how risk averse somebody is. So we do exactly the same thing, but it's cast in terms of these empirical priors, usually precisions of belief structures.
Can I ask a follow-up question, if it is okay with you? So Karl, just a follow-up question. Then what would be the simplest sort of object? I guess human beings are comparatively much more complex in terms of making decisions and so on. So this is, I guess, something related to what Silvia was asking, that when we do not quite have this much, the ability to assign a probability itself requires a lot of complex calculation to begin with. So what would be a simplest object which will be able to do this calculation? I'm just trying to understand the range of applications where it can be applied.
I see. Right. So I think the first thing to say is, when I talk about beliefs, I just mean probability distributions. I don't mean anything propositional or something that somebody's worked out in their heads. I simply mean a conditional probability distribution that is parameterized by the physical state of something. So everything I've said would apply to a thermostat. So the electrical currents in a thermostat would stand in for some belief about the causes of the temperature sensor. And its prior beliefs would be that it would look as if its prior beliefs were that the temperature should be at its set point, and everything that it does and everything it believes is in the service of minimizing surprise in its inputs by bringing the temperature back down to its set points. So then the interesting question about complexity is, well, what's the difference between me or you and a thermostat? And that's a really interesting question. The normal answer to that is that it's the depth into the future that you can that your generative model entertains. So a thermostat can't plan, whereas you and I can. So we now, if I was a physiologist, we now have allostasis. Or if I was in machine learning, I would be appealing to planning as inference. And that's really interesting, because as soon as your generative model or your cause-effect structure that you're trying to secure evidence for has a notion of the consequences of an action or a movement, then it must have it must cover the future. So it requires a temporal depth, which the thermostat doesn't have. And I think it's that fundamental depth and counterfactual richness that comes for free as soon as you consider generative models that could entertain or model what would happen if I did that or that or that. So they're in the future and they're counterfactual. So they have a particular depth, which makes me and you very different from a thermostat. And then you move on to, well, what happens now if we put these thermostats with temporal depth together to play? And then we get back to the questions about what would emerge in terms of sort of coupling these systems together, where they're all trying to infer and plan around each other. And then we get back to game theory. So it's, but those are many moves away from the Bayesian thermostat. But really interesting questions about the nature of the
It
generative
has
model.
a parallel sort of with that self-esteem idea in some sense, that the future planning may not be quite there, but somehow it's locally optimizing, and eventually that leads to some kind of complex organism coming up.